This morning in the Atlanta airport, no one's missing a meal on Mac Wilburn's watch. With 11 restaurants to serve passengers, he's got dining for every destination. And it all started when Mac talked with First Horizon Bank about opening a franchise in the airport. Now it's open for business and cleared for takeoff. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac. First Horizon Bank, member FDIC. Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more. Momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us. This is the Space Nuts podcast, and my name is Andrew Dunkley, your host, and joining me for episode 260 is someone completely the same. It is Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How did we get to 260? For goodness sake.
I don't really know. But it's
Me neither.
It's great. It's really a thrill.
It is. It's fantastic.
And I think we've created something of a kindred community when you look at the social media interaction between people, and I want to send a shout out straight away to my self-appointed police force on the Space Nuts podcast group Facebook page, because they are on ready alert for any infiltrators who are trying to spam us, and they get on them pretty quick. So good job.
Yeah,
good job. Now, coming up, we will be answering questions, which we were going to dedicate the whole episode to, but we've got a couple of things we want to talk about first, so we'll do that. But we've got questions from Richard on the Sunshine Coast, Mark in Newbury in the UK, Doug from Seattle, and Thomas in Orlando. And if you're all going, geez, I sent those questions in months ago. Yeah, we know. They've been on the back burner, and because we don't think we give the text people a fair tilt on Space Nuts, they're all text questions. So we'll get into those and some really fascinating topics too, I might add. Before we get to our first story though, Fred, are you still in lockdown? I heard they're going to extend the lockdown in Sydney.
Indeed we are, yes. We were originally going to be locked down till Friday this week, but now it's been extended till Friday next week, which continues to stuff up arrangements that we've got here. Never mind.
Yeah.
That's all right. It's all in a good cause.
Yeah, I suppose it's unavoidable. They've got to haul this in. They've got to deal with it. And I know it puts a few noses out of joint, but the good news is I'm no longer in isolation. My time is done.
Right. Good, yes, of course, yeah.
Yeah, because I'm not in Sydney, I can go back to the radio station, which sounds nice, but it actually smells rather putrid because the cold weather has driven the mice inside.
Oh,
so
Andrew.
It stinks like you couldn't believe.
God, that's awful.
Yeah,
oh, dear.
I'm fed up with them. I am fed up with them.
Yeah.
They are just, they're not going away, the little
horrors.
Beggars. Now, let's get into our first story. This I heard on the news today on our radio station. It looks like we've got a space race on for young and old, particularly old, because it's not your traditional Russia versus America to the moon space race. This is Virgin Galactic, Richard Branson and Jeff Bezos trying to get into their orbital spacecraft first.
Yeah.
And the way I'm looking at it, the bookies have got short money on Richard Branson at the moment.
Yes, that's right. They have, according to all the various announcements that have been made. Excuse me. So we've got a very esoteric record to be set here. The first billionaire into space with their own spacecraft, and it's between Richard Branson of Virgin Galactic, Jeff Bezos of New Origin. His company is Blue Origin. I beg your pardon, not New Origin, Blue Origin. And so just the quick background that both of these companies are aiming to take tourists on suborbital flights above the Earth's surface to about 100 kilometers. So an up and down trip to 100 kilometers. But they do it in different ways, as we've spoken about before. But just very briefly to reiterate or to recap, Branson's Virgin Galactic operates with an aircraft essentially to take the space vehicle up to round about 16 kilometers, maybe a little bit higher. It's a 4-engine jet, very unusual form, 2 fuselages and a place in between them where you can hang the rocket plane. Get up to 15 or 16 kilometers, release the rocket plane. It fires its rocket motor, which accelerates. It only burns for, I think, 90 seconds. But in that time, it whizzes you up to roughly let me think. Yes, about 1 kilometer per second is I'm just doing the calculations in my head. A little bit more than 1 kilometer per second, which is not high enough to go into orbit, but it's enough to poke you up very rapidly to this height of 100 kilometers or so. And once the rocket motor cuts out and you're coasting upwards, that's when you're weightless. You reach apogee, the highest point, fall over again, and you're still weightless until the rocket plane starts deploying its brakes, which actually means bending up the rear end of the delta aerofoil, and then it lands like a glider. That's the Branson method. The Bezos method with Blue Origin is a lot more straightforward. Your capsule is sitting on top of a rocket, which simply sends you up, once again accelerates you to that, typically a bit more than 1 kilometer per second upwards. The rocket falls away, your capsule keeps on going, and then lands with parachutes once it's gone through the same process, going up to apogee and falling back under weightlessness. Once the parachutes are deployed, then you start feeling accelerations again. The reason why I wanted to mention this, though, today, Andrew, is because the first planned flight now is probably going to be before our next broadcast or our next podcast.
Wow.
With Branson scheduling a flight. I think technically he said not before the 11th of July, but everybody's putting the 11th of July in the diary, oh, that must be it. Whereas the Bezos first flight with Jeff on board is currently scheduled for 20th of July. So the race is on. Who knows whether everything will go well? I don't think it really is a race. And I have to say, both these companies have been extraordinary in the attention they've paid to getting everything right, because this is a difficult thing to do, to take people into space. The last thing you want is an accident. They've already had one. Virgin Galactic lost one of their test pilots several years ago. It might have been 2014. It was quite a while ago. The inside story from people closely connected, certainly NASA people I've spoken to, say, and I'm sure the same is true of Blue Origin, but they say that Virgin Galactic is exemplary in the way it deals with all the issues that need to be looked after. Branson is going to be, I think, the first and paying in inverted commas customer, because even though he owns the company effectively, he's not actually a staff member. So they've had to do all the clearance, the requisite legal clearances to fly with passengers, because he counts as a passenger. And so that all went through last week, as I understand it. So the road is clear for Branson to make his flight. Sometime, my guess is it'll be next week sometime. You never know quite with weather and things of that sort. It will actually be the 22nd flight of their rocket planes, but not the 22nd to reach the edge of space. They've had 4 flights that have done that. The Blue Origin process has been similarly extensive in its testing. The 2 Bezos brothers will be the passengers on the mission, along with a person called Wally Funk. Do you know who Wally Funk is, Andrew?
It rings a bell.
Yeah, she is one of the original Mercury 13 crew members. The team
Wow.
of female astronauts that were trained up and passed all the requisite all the requisite tests and everything for them to be able to fly with the Mercury capsules back in the early 60s. Wally Funk was one of them.
Yeah.
I believe she's 82 now. So that...
I think the reason that name rings a bell is they portray her character in the TV series that Amazon, I think, was running. And I'm just trying to think of the name of the series now. It's just dropped out of my head. But For All Mankind. For All Mankind.
Okay.
Yeah. So she's someone's playing her character in that. Yeah.
Okay, so that there's a link there if that's on Amazon.
I think it's
of
Amazon.
course,
Yeah.
phone's Amazon.
Oh, it might be Apple. Actually, I think it's on Apple.
Okay,
I can't keep up.
Yeah. Never mind. So the spacecraft is the New Shepard. It's essentially an up and down rocket of the kind I've just described. The great thing about the Blue Origin technique is that, like Elon Musk's SpaceX Falcon 9 spacecraft or a rocket, launch vehicles, Blue Shepard lands on its tail. It doesn't just fall back to Earth and go bang. It lands on its tail, and so it can be reused. It's really an extraordinary process, and really interesting that we've got to this point in time where within a fortnight, the two main contenders for space, for space tourism, are on the point of making their first, what you might call, commercial flights.
Yes, it's extraordinary. And of course, you've been to the space drome, haven't you? What the
Spaceport America. That's right.
That's it.
In New Mexico. It's a place called Upham. That's the little village, which I think is amazing. But it's near a town with the extraordinary name of Truth or Consequences. And there's a story behind that. That's the nearest town. And once the spaceport becomes really fully operational, which it will eventually, Truth or Consequences is going to be the place you go and take your hotel accommodation there until you make your flight.
Yeah, they must be thrilled that this is all starting to happen.
Yeah. What they're less thrilled about is that it's taken so long, because I think that spaceport was built probably 7 or 8 years ago.
Yeah.
It would have been, I've got a feeling it was 2014 when we visited it, so quite a while back.
Yeah, but look, you can't really knock them for taking so much time, because safety is the primary thing. So we wish them well, and we'll wait and see what happens, and hopefully all will go perfectly. Sorry, Andrew, I was just going to say, won't it be nice for us to be able to report on something that's been a year in the future for the last decade or so? Absolutely. All right, we wish Jeff and Richard well in their exploits. Now, let's just quickly have a talk about this story. It's to do with Mars, got nothing to do with American or Chinese rovers trundling around on the surface trying to stop P-platers from overtaking them. No, this is about water. And it looks like there may be lakes under Mars' South Pole.
Well, that was the original story, and you and I have spoken about this.
I thought we had
several times.
Yep.
Yeah.
Thought we
Just
had.
to remind you, back in 2018, it was scientists who were looking at data from Mars Express, which is the ESA spacecraft still in orbit around Mars doing great stuff, which was saying that they were getting really strong radar reflections from a layer, I think it's about 4 kilometers beneath the surface of Mars's south polar ice cap.
Yeah.
And that was essentially interpreted as being reflections from a subsurface lake. And there have been others since then, other radar reflections. So the reason for that is that a water ice boundary is quite a strong reflector of radar signals. And so, that's the most direct interpretation. There's a bit of physics that had to be done as well, though, because, of course, the temperature on Mars near its poles it's over 100 degrees below zero. And at least on the surface it is, maybe deep down, because of the pressure of the ice, it's more like 70 degrees below zero. This is Celsius I'm talking about here, minus 70. And so it's not just the pressure of the ice that's keeping the water warm, if it's there, and by warm I mean minus 70 degrees, but also the fact that people assume there will be dissolved salts in it, these perchlorates, which are like a natural antifreeze, and which lower the freezing point of water by a huge amount. So that was the thinking, that maybe that there are these perchlorates in the water and that's why it's there. However, new research, in fact 2 lots of new research, one by I think their university, is it yes, Arizona State University. That's in fact, he's a graduate student who's led this work, which is fabulous. Aditya Kula is her name. I think that's how you say it. Finding first of all lots and lots of similar reflections, but what they're finding is that these are in areas that the physics doesn't work to keep them warm. They're areas that are too cold for that water to remain liquid. And there's another team of scientists at Arizona, once again at Arizona State, which has been looking at what else there might be. And this news came out first. This was released last week. It's that they have worked out that if you've got certain sorts of clays, maybe some metal-bearing minerals, or even really salty ice, slushy ice, you might get the same strong reflections, rather than this being water. So the idea of it being liquid water in lakes has kind of gone off the boil a bit. We're now thinking it might be clays, or it might be a slushy, sort of thick, icy material that's got minerals in it. We're not sure. It's like a lot of science, Andrew. You have these great ideas and you think there's, great evidence for what you see, but because we can't go and touch it, you bring other ideas to bear, and suddenly things have changed. So we really don't know now what this is all about, whether there is just some sort of cold mud down there, or or whether there really is liquid water. And the fact that there are lots, they've got the new work has included many, many measurements that show literally thousands of these higher reflective areas. So if it is water, then it's everywhere, or perhaps more likely, it seems that it might be something else. So we really don't know. It's a really interesting impasse in a way. There's another paper that came out a couple of years ago that once again threw into doubt the idea that just pressure and perchlorates could keep this water liquid. This paper said that the only way you could explain liquid water under the South Pole would be if there'd been recent volcanism heating up the subsurface ice in that region. So it's looking less likely that we've found lakes under the South Pole of Mars, which is a pain because it says in my new book that we found lakes under the South Pole of Mars. Fortunately,
do a last minute edit.
It's not too late. That's right. We're doing the copy editing right now, so I can change that.
Oh, that's somewhat of a disappointment. Instead of crystal clear water, we've got bogs.
Bogs, yeah, that's
bogs.
Right. Swamps. Yeah. Swamps under the ice.
Oh, you can't call them swamps anymore. They're wetlands.
Wetlands, of course. Yes, I'm sorry. Well, damp lands might be what it is, not wet.
Yeah, possibly so.
Yeah.
All right. Well, I'm sure down the track we may hear more about this as they study more and more evidence, and maybe one day mount a mission to try and figure it out for certain.
I'm sure that'll happen.
A lot of ice to get through.
Yeah, there is, yeah.
All right. We'll get on to the questions very soon. You're listening to the Space Nuts podcast with Andrew Dunkley and Professor Fred Watson.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, What are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
3, 2, 1.
Space Nuts.
Thanks for joining us. And don't forget, the Space Nuts shop is on our website, where you can go to, peruse our stock, whether you want a pair of flip-flops or a cap or a hat or a mug or a sticker or a bomber jacket. There's a vast array of material there at the Space Nuts shop, where you can, buy something for yourself or a friend or a hard-to-buy-for uncle. It's spacenutspodcast.com, and just click on the shop button, spacenutspodcast.com, and then click on the shop button to have a look through the Space Nuts shop. Now, I have something very, very important to say. Young Ashley, who sent us those squillions of questions last week, suggested we needed a sticker that says, "I am a space nut." Ashley, I am very, very pleased to report that Hugh thought that was the greatest idea in the world, and he's going to do it. So we will be getting an "I am a space nut" sticker. And Fred, we got a lovely note from Ashley's mum saying thanks for answering all his questions. It seems like we've sparked a lot of enthusiasm in young Ashley, and we're very pleased to have been able to get all those questions answered for him. And we're going to answer some more now. We've got a whole bunch of text questions, and we don't do enough of these, so we'll focus on these today. Now, this first one comes from Richard on the Sunshine Coast, and he says, our current technology lets us peer back to a galaxy 14.2 billion light years away in the infinite universe. If we went to where that galaxy is seen, to the point where it was all those years ago, and peered out again with our telescopes, I assume we would find another galaxy somewhere that is also 14.2 billion light years away. And if we went to where that galaxy is presently located, would we be able to see the same, another galaxy 14.2 billion light years away, and so on? Or is it the case that no matter where we are in the universe, we would always find something 14.2 billion light years away? Or the opposite, is there any place in the universe where we could only find objects less than 14.2 billion light years away? How does this not infer an infinite universe? Could space curve back on itself so that we still have a finite and expanding universe and still be able to peer out 14.2 billion light years no matter where we are? It's all too hard for my head to get around. Many thanks for your outstanding show. Cheers, Richard. He's been really pondering this one, from what I can tell.
It's a great question, and it goes to the heart of how we think the universe behaves. It might be an old report that Richard was looking at, because by today's measurement standards, the furthest galaxies that we can see are around about 13 billion light years away. Although that's not we glibly talk about them being 13 billion light years away, but in fact what we really mean is that we've got a look back time of 13 billion years to them, because their true distance is probably much more than that, because the expansion of the universe is probably more like 30 billion light years. So anyway, that's a detail that doesn't really matter in this discussion, because he's absolutely right that if we could be where that galaxy was, let's say it's 13 billion light years away from ours, and had a look, we'd see the same thing as we see now. We'd see galaxies all around the sky. We would see the most distant ones would be about 13 billion light years away that we could see. And then if you went to another one, it would be the same picture. Now, if you can do that ad infinitum, it suggests an infinite universe. Actually, it doesn't suggest that. What it suggests is an unbounded universe, one that doesn't have an edge. Because you can have a finite universe that is unbounded. If you think of the surface of the Earth, the surface of the Earth is definitely finite, but it doesn't have boundaries, because you can keep going, forever. And that's the point of Richard's last comment, that is space curved back on itself so so that it looks as though. So basically, you could go all the way around and come back to where you started from. The current thinking is that eventually, yes, after a week or two, the current thinking is that it's probably not, that we've got what's called a flat universe. So the geometry of the universe means that it is kind of like the geometry that we've got around us. It just goes on forever. And that, so yes, the answer is we don't know. There are many cosmologists who believe that the universe probably is infinite, or at least unbounded, just to come back to that idea, but maybe infinite, because if it's a flat universe, it's not curving back on itself. So it's really at the forefront of physics, and Richard's struggling to get his head around it is about the way I do as well. One of the point is that we only know what we can see from our vantage point, and what we find is what we call an isotropic universe, one that's the same in all directions. It could be that as you move through that universe, maybe that would change. Maybe you would find places where the density of matter was different, and that would cause the universe to have a different curvature, because it's the matter in the universe that gives it its curvature. When you're thinking about, space bending back on itself. So from our perspective, it looks as though it's infinite, but we can't answer for the rest of the universe. We can only talk about our bit.
So Richard, Fred just took 25 minutes to tell you we don't know.
No, to tell him he's right. He's right. We don't know.
Okay, that's a fair enough assumption. Yes. No, but it is, I suppose, one of the biggest mysteries of the whole existence of existence, because these are the questions we're pondering and the questions we're trying to answer. And, we're chipping, as I've said before, we're chipping away at these things. And every time we chip something away and go, aha, we answer a question and we've got three more
the chips they get bigger. It's a bit like the Sorcerer's Apprentice, as you chop up one question, 20 more appear.
Yeah, it is like that. Very much so. Anyway, Richard, there you are. That's the latest that we have on the ever-expanding universe. And thank you for your question. Now, we'll move on to the UK with Mark in Newbury. Just a short and sweet question. We know the hydrogen fuel in our sun will run out in approximately 5 billion years. What controls the rate of fusion between hydrogen atoms to prevent the fuel from being burned up much faster to the point of happening instantly, or slower than the current rate? The price of fuel out of the Middle East, I think, would have something to do with it. But I suspect...
No, you're on the right track. So the fusion process is essentially that basically hydrogen nuclei, which are protons, in fact, I think it takes 4 hydrogen nuclei to fuse into one helium nucleus, and this is the process that drives the energy of the sun, and it's the figures I'm looking at here. About 0.7% of that fused mass is released as energy. So it's a process that it's discrete in the sense that it needs a certain number of hydrogen nuclei to make the helium nucleus and release the energy, and that process has got it's got its own clock. In other words, it always takes the same length of time. So that, I think, explains part of the question. It's Mark's question, isn't it? So the rate of that fusion is not a random thing. It depends on exactly which atoms are coming together and how the energy is released. It's a gamma ray photon that's released. That is something that takes a specific time, and that's what causes the thing to sort of have this built-in clock with it. And then you've got to lump, as well as that, you have to lump the amount of hydrogen that's in the sun. So the bigger, actually, it's not intuitive either, because the more hydrogen you've got, the faster it burns. It's a bit the wrong way around. You'd think the more hydrogen you've got, the longer you would have. But it's the massive stars that burn through their hydrogen most quickly. The current rate of hydrogen burning is about 600 million tons per second. It goes through. And of that, about 4.2 or 4.3 million tons is turned into energy. And it's that direct fusion of that, that amount into energy that gives us the heat and light of the sun. That's going directly from mass into energy, being multiplied by c squared, by E equals mc squared. So that's why you get so much energy from what is not that big an amount, 4.3 million tons per second. I mean, it is a lot, but it's when you think of the solar system bathing in the heat or basking in the heat and light of the sun, that 4.3 million tons per second gives a hell of a lot of energy.
Oh, yeah, absolutely. You can see it happening up in Canada at the moment with some of the record temperatures they've had. Amazing. That is just extraordinary. Right. What that record temperatures, as in multiple degrees above their previous records. Smashed. We're not, there's some places that had temperatures 12 degrees above their previous records. I mean, they're just massive numbers. And I think I saw a story this week about, now where was it? I can't remember. But one of the, I think it was one of the Greek islands or something, it had the biggest fire in history this week. So there's a lot of energy beaming down on us, and it's quite destructive at times, unfortunately. So yes, it is. There is a reason. It's and it's an interesting point that the bigger the star, the faster it burns.
Yeah, that's exactly not what you expect. I need to look into that one.
Well, it seems logical to me because it's the same with cars. So the bigger they are, the more they burn. Yeah. Anyway, hope that answered your question, Mark. Thanks for sending it in to us. I know you've probably been waiting for that one to be answered. You've probably given up waiting for that one to be answered, but we got to it. Anyway, coming up, we're going to infinity and beyond with our next question here on the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
I'd like to say thank you again to our patrons, and if you would like to become a patron of the Space Nuts podcast, you can do that via our website, spacenutspodcast.com, and click on the Support Space Nuts button, and all the options are there, whether you want to do it through Patreon or Supercast or PayPal or the Space Nuts Shop's an option. Just puts a bit of money in the kitty to keep us ticking along. We're not going to be able to pay for a trip into suborbital space with any of the gentlemen who are attempting to do so at the moment, but it'll enable us to tell you about it. That's what it's for, and it keeps things rolling. So thank you to our patrons, appreciate it, and to our supporters on social media who are very, very active on Facebook particularly, but also on YouTube, where you can see what we're doing as well as listen. And, how incredibly exciting is it to see our faces and the back walls of our offices?
Lovely.
What's the bowling pin all about, I'm wondering? That was a long time ago.
I'm wondering that too. Yeah.
Anyway, let's. I did win a bowling tournament once. Believe it or not,
doesn't surprise me.
I've done some weird stuff. Okay, let's move on to our next question. This comes from Doug in Seattle, Washington. Hello, my favourite pair of erudite astrological Aussies. My question is for Professor Watson. No offence, Andrew. None taken. I understand if I understand the process correctly, What is when a sufficiently massive star collapses and neutron degeneracy pressure is overwhelmed by extreme gravity? I practiced that and I still couldn't get it. It collapses further and becomes an infinitely small point with infinite density, a black hole. Conversely, in the earliest moments of our universe, the total mass of the universe existed in an almost incomprehensibly small area that expanded to the universe we see today. How did the universe expand? Why is the universe not an infinitely small point with infinite density? There was a big bang.
Well, that's right. And exactly. You've got the answer in a nutshell there, Andrew.
There, Doug.
Let me put a bit of detail on
yes,
that.
I think you should.
So we're talking now about events that took place within the first 10 to the minus 33 of a second. Because beyond that, we kind of understand how things work, about the formation of hydrogen nuclei, which happened within the first 3 minutes. That we kind of understand it from that fleeting moment after the Big Bang itself. But the first 10 to the minus 33 of a second, I think that's the number. It's something like that. We've no idea what happened. Clearly, something did. Some physicists have theorized that you could get, and this one does my head in, Andrew, you could get an instability in nothing that results in the Big Bang.
Okay.
Yeah. So you can't have nothing that just stays nothing. It turns into something else. That's one of the ideas.
It's starting to sound like a Monty Python song.
Oh, it is, yes. In fact, that's right. Especially where the big boot comes down and squashes them all at the end of the graphics at the intro with the raspberry. It's a really good question. It's Doug, isn't it? Our question. I don't have the question in front of me. The thinking is that the Big Bang did come from a singularity. Now, a singularity is exactly what a black hole is. It's a point in space with no dimensions, and that gives it infinite mass. So, likewise, we think that the Big Bang universe was itself a singularity that somehow detonated into what we see today, and it's just crazy to think about how that could happen. If you've got something that's less than the size of a full stop on a page of the Hitler paradox, how is it going to turn? Well, maybe that explains how it turns into a universe. I don't know, but yes, it doesn't. It's quite counterintuitive, and as I said, the physics that we understand can go back a long way. Can go back to this brief instant after the Big Bang, but what happened before that is a closed book to us at the moment. And theoretical physicists have a good stab at it, like saying, oh, yes, it's a point in nothing that became unstable. And I have to say, I haven't looked at the mathematics of that. And if I did, I doubt I'd understand them. So your question is a good one, Doug, and it baffles me as much as it baffles you.
Could it be, Fred, that there was a Gnab Gib that created a singularity,
yes, yeah.
And then that just couldn't hold, and boom,
maybe
she went again?
Exactly. I mean, that is that's what you might call the cyclic theory of the universe. That it was a previous universe collapsing, and the collision of that collapse is what caused our universe. It still begs the question: what happened at the beginning, though? Where did the first one come from? And you've got like old Roger Penrose's ideas that universes do come from black holes. If you get black holes that are massive enough, they become unstable and they turn into a Big Bang, which in many ways is a bit more logical than an instability in nothing. The bottom line is we don't know, and you've always got this question. Okay, suppose it's a black hole becoming unstable. What formed the black hole in the first place? There must have been a universe in existence there to start with. So where did that come from? And I have to say, as time has gone on over the of the centuries of my life, I've begun to suspect that there are some questions that we will never be able to find the answers to. Not because we don't have the physics, but because we aren't equipped with the thought processes that might lead us to understand them. I know that sounds wishy-washy and a bit ethereal, but it
just sounds like my entire school year.
yeah. Some of mine was like that as well. My worst moment at school, Andrew, believe it or not, was in physics. And great, he was a fantastic teacher, but we all, he was a bit short-tempered and a bit grumpy, and so he wasn't very popular. But he really laid into me once over my physics homework because I was trying to add up calories and things of that to make the right answer for the amount of heat that you got in a bucket of water or something. And he tore into me when he got to it, and he said, "Why didn't you add the date in as well? You might as well have done."
But I did have a couple of teachers like that.
I've never said this on air before on radio or anything, but his parting. I went to what was a fairly good school. It was a state school, state run, but it was it had good teachers and a good reputation. And at the end of his tirade, he said, "You try to make out you're a fool, but you can't be a fool, or else you won't be at this school, you damn fool." What? So there you go. There's some things that we will never be able to understand, like what was going through his mind.
Yeah, exactly so. Reminds me of an English teacher we had in high school. I adored him. He was he inspired me in many ways, and I got to meet him many years after his retirement and gave him a copy of All I See Is Mud because I just wanted to thank him for being my teacher. But he was tough. He was really tough, and nobody gave him cheek. And if he just heard a ripple of attitude, he would just look at them in the eye, and you would wither.
Yeah.
And he would say, "Do it again, and I'll throw you through the wall." And he meant it. And we were on the second floor. Yeah. He was tough.
Good on him.
But he was fair, and he was a good teacher.
A lot of them were.
Really loved him. So that was Doug's question in Seattle. Fabulous question too, Doug. Thank you. Yes, it continues to be one of the great mysteries, really. But, I think we'll figure it out by next week. Now, let's move on to our final question in this episode 260 of the Space Nuts podcast from Thomas in Orlando. I've been to Orlando. I loved it. Too many alligators. Why is the speed of light a constant? What is it about photons that makes them travel at only one speed? Does space-time have meaning to a photon, or is it everything at once? Thanks, Tom in Orlando. I know that photons can be affected by gravity, but I suppose in real terms they travel at one speed.
So the bottom line is, in a vacuum, they travel at one speed. Right. 300,000 kilometers per second, a foot per billionth of a second. If you're in the imperial units, this much in a billionth of a second. Can't see it. So gravity does affect light, but it doesn't slow it down. What it does is it redshifts it, so it changes its wavelength. That's the effect of gravity. But it's a really good question, and it's a little bit like the last one we've had. We don't really know, and in many ways, the speed of light, it kind of sacrosanct in that it doesn't change. It is relentlessly constant in its value to the extent that space and time change around it. That's what relativity is all about. And the constant speed of light is one of the basic premises of relativity, special relativity. If the speed of light is constant, then you're going to have weird effects with space and time actually deforming. And we talk about that frequently. So it's almost like it's like a bedrock of constancy, which was spotted first by James Clerk Maxwell when he did his work on electromagnetism in the middle of the 19th century. He kept coming out with this with this quantity, and it's to do with electrical charge. And I think he gave it the letter C. We call the speed of light C. I think it was Clerk Maxwell who did that. And he couldn't get rid of it. It was always the same. It was this number that kept popping out. And it was almost like, oh, wait a minute, that's the speed of light, because that had been measured by then. It was so it was at the absolute root of all the electromagnetic studies he was doing. And that's a bit like what it is in physics today. It's totally fundamental. There are just a few physicists who think that they have spotted evidence of it changing at very great distances. John Webb is perhaps one of the principal proponents of this. He's a scientist at the University of New South Wales. Before COVID-19, John was always somewhere else. He was always giving a colloquium in Cambridge or Princeton or somewhere. So they used to call him the World Wide Web.
Oh, that's right. I've heard you tell me that before. Yeah.
It's probably slowed him down a bit with COVID-19. John thinks that, I'm not sure whether he still thinks this goes back a decade or so, that in the spectra of quasars, the emission that is emitted by these extraordinary, black hole sources in the distant universe, when he looks at the spectra of quasars, he thinks he sees a shift that could only be explained by one of the fundamental quantities moving. And actually, I think it could also be the charge on the electron that is different at those really long look-back times, or the speed of light. But the data are very, very near the limit of detectability. I have never really thought that there was enough information there to make that claim. And I'd be interested I should try and catch up with John sometime, have a talk to him, see what he thinks these days. Because I probably couldn't understand any of the papers he writes. If I can catch up with him when COVID-19 comes, I'll probably find him in Murmansk or Reykjavik or somewhere like that, and we'll have a chat about it. Anyway, it's a basic fundamental of the universe. And to ask why it's constant is a really good question, and I don't know the answer.
There you are, Thomas. Once again, we are unable to help, but we do our best to be adequate.
It's the edge of knowledge. That's kind of where we've got to. Yeah.
And you know what? It's probably not surprising that people are asking questions like that, because we're all wondering about it.
Yeah, they get it.
So they throw the questions at you, Fred, because you're so astute and should absolutely know the answer to the unanswerable questions, but forgivable that you don't quite have it all.
Not quite. I do have one piece of information, Andrew, that is real, and it's a stop press item.
Oh.
We can stick it in, which I've just read. And that is that Ingenuity has made a successful 9th flight. It covered a total of 625 meters. That's an enormous distance.
Yeah.
So they've really pushed it to check the limits within which this little helicopter can fly over the surface of Mars. It was 166.4 seconds. It reached a record top speed of 5 meters per second. So fantastic stuff. Well done, NASA. Well done, the Ingenuity team.
They keep pushing the boundaries, don't they?
They do, and it comes up good every time. They've done a great job with it.
Terrific. All right, well done. And thank you to everybody who pitched some questions for us this week. Even though we were a bit slow to get to some of these, we appreciate them all. And there are a few more that we might try to trickle through in coming weeks. And if you sent in audio questions expecting them to be on this week, communications breakdown, basically. I forgot to tell Hugh I wanted them. I'll take the rap for it. I will. No hiding the truth. But anyway, we will get to them. They will come up in a future episode for sure. That winds us up, Fred. Thank you. Oh, by the way, don't forget, if you want to ask us a question, go to our website, click on the AMA tab. You can send us a text question or an audio question. It's a pretty simple interface. And we're working on other ways of getting questions to us. There might be a new process in the not too distant future. It just depends how things go. But spacenutspodcast.com, of course, our website, which brings us to the end of the episode. Thank you so much, Fred. Good to see you. Good to talk to you.
Yeah, great to talk to you as well, Andrew. And we'll try and be more definitive about some of our answers next time.
Well, they should ask us easier questions. This is what I always thought when I was
it's great.
at school.
You know, what an audience whose questions are right at the forefront of knowledge. It's brilliant stuff.
Indeed. Yes, indeed.
Yeah.
Take care, Fred. We'll catch you next week.
Sounds great. See you, Andrew.
Bye. Fred Watson, astronomer at large, and to Hugh back in the studio, thanks for pushing all the buttons and pulling all the strings and, you know, using all the super glue to keep us going. And from me, Andrew Dunkley, as always, thanks for listening. We'll catch you on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.